All right, so let's consider the concept of a limit. If we think about a limit in day-to-day terms, you might reach the limit of your endurance, or you might reach the limit of the amount of money that you're able to spend, or so really what we're saying is you reach a particular value. You're approaching it, you're getting close to that limit, you're approaching that particular value, and then you sort of reach it. And I guess mathematically that's what we're sort of talking about, okay? So if we talk about the limit of a function, we're actually talking about the value that the function approaches. Now, it may not be a maximum or a minimum, it's just the value that this function approaches at a particular point, okay? So let's look at so I guess to extend that a fraction further, if we have a function, if we have a function here, and we're talking about that point there where x is equal to, maybe x is equal to 3. Now, as I approach x equal to 3, this function approaches that value. Yeah, and then when I actually reach 3, well, that's the value that we reach. So that value that we reach, that's the limit of the function. And that's the terminology we talk about. As the function approaches. So as the function approaches 3, the function approaches, maybe that's the coordinate 3, 9. Okay? So the function approaches that value. All right? So the limit of a function f of x is the value that f of x approaches as x approaches a given value. All right? So notation wise, the limit as x approaches a of the function f of x is equal to p. So if you like, that's the x value there at a, and p is the y value. All right. It is possible that the function may not be defined at that point. Yeah. So if we were to consider a graph where we have asymptotes, it might be just a little bit, maybe that's the line y equals 3. So, and in fact, I won't even do the top and bottom line. We'll just keep it like a hyperbola. So, as x gets further and further along, the y value gets closer and closer to 3, doesn't it? But it never actually reaches 3. Yeah, so you've got concepts like that to think about. But let's go back a step and let's just evaluate the notation. All right. So if I've got a function f of x equal to 3x squared, the limit as x approaches 2 basically means we just substitute the x value in. So the limit as x approaches 2 of 3x squared, substitute the 2 in, we get 12. All right. Now, if it's not defined at that point, it means that there might be some simplifications that we can do. All right, so let's consider the next one. The function f of x equals that. Consider the limit as x approaches 2. So straight away, if I put x equal to 2 into this function, I get 8 minus 10 plus 2 over 0. So what's that going to give me? Whatever it is, it's... actually, it's 0 over 0, isn't it? Of course it is. Okay. If we get the form 0 over 0, more than likely, there's some cancelling that can happen. Okay, so if I was to factorise that f of x expression, the top becomes 2x minus 1, x minus 2. So this function can now be written as the limit as x approaches 2 of 2x minus 1, x minus 2 over x minus 2. Those x minus 2's cancel. So this function simplifies to the limit as x approaches 2 of 2x minus 1, which is 4 minus 1, which is 3. So whenever you get the format 0 over 0, it means that there's some cancelling and simplification that can take place. Sometimes you might just get 0 over 3, or you get 0 as an answer. That's fine. The function is allowed to approach 0. And sometimes the function can be undefined. You might get a 3 over 0. All right. But if we get that 0 over 0 form, it means that we can do some cancelling. All right. A few more examples. As x approaches 0, I put 0 into the function. 3 times 0 squared plus 2 is 2. Fairly straightforward. If I go to b, again, that's one of those ones where if I put 4 in, I get 16 minus 16 over 4 minus 4. I get 0 over 0. So factorise first. If I take x out the front, I get x minus 4 over x minus 4. X minus 4's cancel out to leave me with x. So the limit as x approaches 4 of x is equal to 4. Again, same sort of thing. If I put 2 into the top line, I get 4 minus 2 minus 2, which is 0. 0 over 0, which means I can factorise. And typically that's your first step anyway. Factorise your top line, x squared minus x minus 2. There's a common factor there of x minus 2 that will cancel out. So I end up with the limit as x approaches 2 of x plus 1, which is equal to 3. All right. D, there's, I guess, no divisions there, so we just substitute our values in. All right, so if I put 3 in that, I'll get 6 minus 3 over 9 plus, or times 9 plus 2, I should say. So 3 times 11 is 33. The next one, again, it looks like there is some factorising there that could take place. If I substitute 4 in, I get answers. Negative 2 over negative 9, which is 2/9, and that's fair enough. If I factorise first, I might find it might be a little bit easier for me. X minus 5 is a common factor to top and bottom. They cancel, so I end up with x minus 2 over x plus 5, which is 2 over 9 also. All right. So when you've got that polynomial expression, it is probably not a bad idea if you can see a simple factorising that can happen, to do a bit of factorising and then simplify and substitute in. Obviously, the limit as h approaches 0 is no different. Yeah. So the limit as h approaches 0, 4h minus 2, we put h equal to 0, end up with negative 2. Again, we're back to an x, put x in there, we get 2 by 3, which is 6, times 9 plus 2, which is 66. And then finally, if I put 3 into that expression, 15 plus 2 over 3 minus 2 will give me 7e. All right, so that's how we evaluate a limit. All right. Now, the next part then talks about continuity at a point. What makes a function continuous? Now, our formal definition, or our practical definition, I should say, can be really quite straightforward to explain. If you can draw the graph of whatever it is you're looking at without taking your pen off the paper, it's continuous. If, on the other hand, I've got to lift up my pen to draw the graph, well, it's not continuous. Okay, so that's a really simple definition of what makes a graph continuous. Okay, we can talk about, for a function to be continuous, the graph has to be defined at the point, and then as we approach that value, I guess the limit has to exist, and then the limit that exists has to also equal the function value. Okay, which sounds a little bit complicated, but it's just some nice mathematics.